Okay, so we learned about prepositions, and we learned that a preposition is either true or false. And now we want to define more precisely those connectives. Okay, so if I have P as a statement, okay, so now I know that P is either true or false. Yes. So I want to define the negation of P a little bit more precisely. So what do you expect? Negation of P is a statement which has the opposite value. Yeah, so for example, if I say that this is P, this is common, that this is called the truth table. So if I have a preposition P, then it is either true or false. But then how do I define this? I would say that the value of the truth value of not P is F if it is true, and it is true if it is false. And so that is the case of negation of a statement. And for example, of course, when I say 2 is a prime number, its negation, you can say this is not the case that 2 is a prime number, but it's not plain language. You would say that 2 is not prime. Or sometimes if you have more mathematical knowledge, you might say 2 is a composite number. Okay, if you really know composite is the negation of being prime. Okay? And then, so this is very simple. So let us not spend some time on it. And then I have another connective. So do you remember another connective, which I read it as and this is called conjunction. So when I say I have two prepositions, P and Q, and I put this symbol between them, I read P and Q. Okay? So now I want to set up the truth table of this compound statement. So we can, if you want, you can consider this the definition of P and Q, this table, okay? But then this is important to understand. If I want to set up a table of this compound statement, because this is a preposition, it has two possibilities for it, and it also has two possibilities. So in total, if I want to consider all mutual combinations, how many combinations I can make? Four, because I would say this is true or false, this is true or false. So in total, I have four possibilities, yes? And this is this way that you can construct. So I have two atomic prepositions, simple prepositions. This has two and this has two. This is the structure, this is the algorithm. If you follow, you always consider all possible cases. So here, I say that I have two prepositions, so I write 2 to power 2, so it becomes 4. This is two, this number is always 2. This number is the number of atomic prepositions that you have in the compound preposition. And then you write 2 to the power of 2, it becomes 4. So this table will have 4 rows. Yes. So then how do you do that? 4 divided by 2, it becomes 2. So you write T, T, F, F. So 2 times T, 2 times F. And the next one, divide this process by half. It means that if you have 2 times T, 2 times F, now make it 1 time T, 1 time F. So it becomes TF, TF. And now look, am I considering all possibilities? Yes, because one possibility is that both of them are true. One possibility is that the first one is true, the second one is false. One possibility is that the first one is false, the second one is true, and the final possibility is that both of them are false. So in this case, in this way, I am really considering all possible scenarios. Okay, of course, I can write P and Q here and just write the last column for you as the definition. But because this is mathematical logic, let us try to understand how we should set up this based on your intuitive idea about the word and. Yes? So for example, let me say that P is 2 is a prime. Okay, and then Q, 2 is rational. Okay, so let me ask you, what about the truth value of the first one? True. It's true. The second one? True. So if I say 2 is both prime and rational, what do you think about my compound sentence? Is it true or false? It's true. Yes, it's claiming two true things. Okay, so in the case that T and T happens, intuitively from what you know about and, you expect that the value is T. At the end, I can consider this the definition of conjunction. Okay, but let us say 2 is a prime number, 2 is an odd number. Okay, is odd. And then I say 2 is a prime and odd number. 2 is both prime and odd. What do you expect about this? To be true or false? It's false. Yeah, so intuitively you understand that in all other cases, it should be false. So this is, if you want, you can consider, this is the truth table of conjunction. So I will talk about this more formally later, but do you think the sentence P and Q intuitively for the time being, because I haven't defined these things, and Q and P are equivalent somehow or not? It seems to be equivalent, okay? But I found a nice example that it seems that in normal usage of English it might not be the case. I couldn't find it. It was an exercise in the book. So the sentence was this: I got sick and I go to a doctor. Okay, and the other way around, I go to the doctor and I became sick. Okay, so in normal language, they are exactly different things. You know, it means that the second one is the doctor made you sick, something like that. Okay, but anyway, this is why we want to avoid in mathematics as much as possible from the keep distance from the normal language. Okay, anyway. Okay, now let us go to disjunction. Okay, so disjunction, so I want to understand this P or Q a little bit better. Okay, so here, if I want to be like that, so disjunction, this means this is red or, and then this is called disjunction, and I want to set up a table for it. So you know that because it's still, so I have P and Q, and I want to write P or Q, and because I have two prepositions, the algorithm is the same. I don't need to think about here, I just consider all the cases. TF, TF. Okay. So if I say P is a prime number or T is an odd number, what do you feel about the truth of that? It's true, yes, because of course one of them is not true, but the other one is true, and you are saying or, yes. So it seems that this should be true, this should also be true. If one of them is true, the other one is false. Because we are using or, then it should be true. For the case that two of them are true, what do you think? It's true. And of course, if I say both of them wrong, two, what do you say? What?
2 is not a prime.
2 is not a prime, and 2 is odd. Okay? Or 2 is odd. Both of them are wrong, so it should be F. I mean, these are easy to understand, yes. But at the end, you have to have this in your head.
So,
yes.
if or was exclusive, then the first one would be...
I want to discuss about it. So this means that you see, when you say or in mathematics, so let me write that in math, or is always inclusive. Yes. So what do I mean by the word inclusive? It means that it is true if both of them are true, or one of them is true and the other one is false. Okay. Sometimes in everyday language it is exclusive or. For example, I say to my kid, okay, either I buy you an ice cream or a chocolate. So usually it means that decide. I will not buy you both. So, okay, so exclusive or, there are some symbols for it. Sometimes people say this. Okay, this is an exclusive or. But this is not one of the fundamental ones. Okay? So in principle, exclusive or should be able to write exclusive or in terms of the previous connectives. But let us not go through it yet. But I want you to understand, when in mathematics I say or, it means either the first one, not the second one, or not the first one, but the second one, or both. This is always or, yes.
Because like in a normal conversation, the inclusive or would be more of an and or. Like, I'll
Yeah,
buy
something.
you a chocolate and or an ice cream.
Yeah, something like that. Yeah. Yeah. But this is important. No one will mention to you that or is inclusive in mathematics. When you are dealing with mathematics, or is always inclusive. Other expressed differently. Yes.
So if it was exclusive or, the first one would be false.
Yes, let me write that one as well. Exclusive or PQ. This is the symbol some books use. Put a little bit bar behind that, but this is always the same. So because we have two, it'd be TTFF, and this is TFTF. Okay, so in this case it is true. Yes, but then.
No, that would be false.
Yes, sorry. That one is false. This one is true. That one is true. Yes.
This one is false.
That one is false. Am I right? Yes. Because this is read either P or Q, but not both. Yes. This is the way that you read this symbol if you want to. So if both of them were correct, then it means that this is false. Okay. So, but I want to understand that whenever in mathematics we use the word or, nothing else, then it is always inclusive. So it means that for some reason, if you're writing your article or whatever, and you mean this kind of or, then you have to emphasize that by writing this explicitly. Okay, but not both, something like that in your sentence. Okay, any questions here? The next connective that I want you to study about this today is this conditional one. So I would read it as if, so let me write it with little I, if, then, yes? No, if like that, if something, then something. Okay, so this symbol is just the arrow from left to right. And this P, if P then Q is called a conditional. So remember, this is a new preposition. We had two prepositions, we combined them with this, and then this is a new preposition, which is called the conditional. Okay. Okay, this is a little bit more problematic, but you know that the first two rows, the first two columns should be identical, because we have still two prepositions. So I would write TTFF, and I would write TF. And then here I would write if P then Q. Okay, let me try to understand this one a little bit better. So I would say that, let me give you a sentence. I would say that if you pay me 100 crowns, I will give you my book. So let us say that is our contract. If you give me 100 crowns, you give me 100 crowns. I give you
No.
my book.
This one not.
Okay, so if P then Q, this is our contract. Yes, so we sign it. The problem is that I want you to feel it. Don't look at this one, because this is a little bit sometimes confusing for students. If, let us say, this is a contract, we sign it, and you are the person who are supposed to do something first, you have to give me 100 crowns, then I will give you my book. This is the agreement, okay? In one case, you will take me to the court, and I want you to understand, because still we have these four options. But only and only under one circumstance, yes, you will take me to the court, yes? And what is that?
If you give 100 crowns and you don't.
If you give me 100 crown and just I run away, yes, I don't give you my book. So in that case, you are annoyed, yes? So I want you to see that if T happens, I mean, if the first statement is true and the second one is false, you feel bad. Yes, so it means that this is F. And is there any other scenario that you are pissed off? No. Do you agree? So that is why I'm thinking. I'm telling you to think in that way, because you might resist a little bit still. Okay. So this is the only way you feel something bad has happened. It's not according to our agreement. So it means that if you really understand that, it means that other scenarios should be T. Yes? So this is T, and this is also T. Okay? So let us analyze that. If you give me 100 crowns and I give you the book, you will not take me to the court. Yes? If you give me 100 crowns and I don't give the book to you, then you will take me to the court. That's F. This one is also understandable very much. I mean, the hard part sometimes is this one. So this one, if you don't give me 100 crowns and I don't give you the book, it is true because nothing strange has happened. Yes, it means that the first statement, our agreement is not violated. Because our agreement was based on that. You give me 100 crowns, I give you my book. Okay? So if you don't give me 100 crowns and I don't give you my book, there is no violation in our agreement. So it should be true. Okay? But this one, what happens?
You don't give 100 crowns, but you give me the book anyway.
But I give you the book anyway. Okay? So this doesn't mean that our agreement is violated. It somehow means I invented a new agreement. Yes? First, I wanted to give you my book based on you paying me 100 crowns. Now I said that, okay, you don't have 100 crowns. Okay, no way, you're my friend. Take my book. It is some kind of contract. But the point is that I am not violating our agreement. So this hopefully is understandable for you. Yes? So this is what you want to understand. And there are some names for it. So this one is called the premise. Yes? And or sometimes people call it assumption. Or it doesn't matter. And then this is called conclusion. Yes? Or sometimes we say necessary and sufficient conditions. Okay, we say P is a sufficient condition for Q. Okay? So P sufficient condition for Q. What does it mean? It means that if I see 100 crowns, it is sufficient for me to pass you my book. Okay? And then, what do you think Q is called with respect to P? It's a necessary condition. Yes? So Q necessary condition for what? P. Yes, what does it mean? It means that if you give me 100 crowns, I necessarily have to give you the book if I want to stick to the agreement. Okay, so these are the words. I mean, if you want to understand it better, sometimes people memorize it in that way. Necessary condition is from the other side to that side. I'm not very good about these. I'm not very fond of these kind of things, but I want to say that P is sufficient condition for Q and Q is necessary condition for P. Even though sometimes people read it as P implies Q, I don't like this because if P then Q is a statement which can be true or false. But usually the word P implies Q somehow means the truth of P logically gives rise to the truth of Q. Most of the logic books, I mean, the past books doesn't differentiate these two, but I think it's good to differentiate them. So this is why I will use these notations, and then I will use this notation. Of course, sometimes I myself get confused, so I use them interchangeably. But let us at least understand there is a minor difference between these two notations if you want to be more precise. So this one I will read P implies Q, meaning that if P is true, logically gives rise to the truth of Q. Okay, for example, let me tell you something tangible, relatable. So for example, let me say P is 2 is a prime. Yes, and let me write Q, Stockholm is the capital of what? Of Sweden. Okay, so let me write this sentence. I mean, of course, in in normal language we don't have these kind of things, but I want you to understand. In logic, this is completely sensible. We can say, how do you read this? You read it as if 2 is a prime, then Stockholm is the capital of Sweden. So yeah, in normal language we will never come up with this kind of combinations, but in logic might be happening. But now I'm asking you, what do you think about the truth value of these compound statements? I had 2 atomic statements. Now I combine them with this connective arrow, and then I'm making a new statement, and I'm asking you about the truth value of this compound statement. What's your answer?
It's true.
It's true because the premise is true, the conclusion is also true, so that's true. But in this case, I don't like to write this symbol. I really want to write this one because this means that if 2 is a prime, then mathematically, logically, or whatever, okay, then Stockholm is the capital of Sweden. It doesn't logically implies that. So I would say that I really want to avoid this here, even though in a lot of, in advanced logic books, they really differentiate because they have to be very, very strict. Okay, but I mean, sometimes people use this for that. So if you get, so then you will see that this table is replaced by this arrow, which I don't like it. So let us try to learn things a little bit more proper and precise. Yes?
Because connectivity and causality aren't the same thing, right? Because 2 is being prime is not the cause of Stockholm being the capital of Sweden. Right?
Yeah, somehow like that.
But
or might be. I don't know if for me it is not implication, but I don't know in the future if you come up with a model that implies that okay, if prime is, then I can prove this, then of course this can be a true statement.
So that's why it's more of like it's more of a subjective difference than an actual like objective one.
If you want to be extremely strict, yes.
Like
because might be in the future one genius come up and find a way to go from there. So let us say that if let me ask you one question. If you are doing a mathematical proof and you want to use arrows, which arrows you use? Which arrow you use? I mean, this one or that?
The lower.
The lower one, because when you want to prove a theorem, you start with an assumption, and when you say from this assumption I go to the next, what you really mean is that the truth of the first one really implies the truth of the second one logically in the framework of that part of mathematics we are working in. Yes? Is that right? Okay. So yeah.
Say that the double arrow like implies that the premise is true, or like that you only use it when you know that it's
something like that. Yes.
Or like it's for the purposes of
something like that.
These notes.
Yeah, might be I can come back to this a little bit later after I define more things. Okay. And then the last connective that we want to study is biconditional, double-sided arrow. Okay, and I told you how the double-sided arrow is actually read. Okay, so the double-sided arrow. Okay, so let me review this once more. So, if P then Q is false only under one circumstance. What is that? The premise is true, but the conclusion is false. So remember that. Okay, so now let us go to biconditional. So this double-sided arrow is read how? If and only if. IFF means if and only if. And then I say P if and only a Q. Okay? Okay, so again, if I want to draw the truth table for it, I have two statements involved. So the first two columns are identical as before. Okay, so intuitively, what do you think I will write here? Yes?
True.
The first one, true.
True. No, and false.
Why? Can you feel it?
Yes.
Because you say if and only if. Yes?
Yes.
Okay? This is false.
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 True.
True again. Yes, exactly. Because this means that if and only if means that if this is true, if and only if the other one is true. Yes? Is that understandable for you? I can't define it, by the way. By the way, if you go a little bit advanced logic, there are only two connectives involved. One is not and the other one is and. All of them we should be able to write all other ones in terms of only these two. We can talk a little bit about these things, but let us put a little bit, start a little bit about the lesson and then we talk about it. So in some books, can you yourself define this arrow intuitively, okay? Can you define this arrow based on a conditional and and? So P, if and only, some books they define this. By the way, I put 3 arrows for equivalency. I will talk about them later. So this is how it's defined sometimes. It means if P, then Q, and if Q, then P. Okay? So this means that, can you say this was, if it was one-sided arrow, P was a sufficient condition for Q. Q was a necessary condition for P. But what do you think we'll say, or I will say here, P and Q? P is, because of this, P is sufficient. Because of the other way around, P is necessary. So I would say P is a necessary and sufficient condition for Q, or Q is necessary and sufficient for P.
Or doesn't necessary override sufficient in a way?
No, that's the whole point. Necessary and sufficient are different things. So that's good that you told me about that, because I mean, if P is this one, okay. By the way, this one. If I just change these two, I think I talked about this in Math 5, but this is called the converse, okay? Not inverse, the converse, okay? And then they are not exactly the same thing. None of them will imply the other one. So here, P is sufficient for Q. Here, Q is sufficient for P, but they are not the same things. Yes? For example, what is a good example for this? For example, let us say that x is a real number, and I say that x is 2. If x is 2, then x to the power of 2 is 4. If I know x is real, okay? So, x being 2 is sufficient for x squared to be 4. Because it means that whenever x is equals to 2 is true, then x squared is 4. But if I write the converse, what happens?
It's not sufficient.
Yeah. This is not correct. Because if x squared is 4, if I know x is a real number, there is no guarantee that x is exactly 2, because there is another possibility for it. So in this case, x equals to 2 and x squared equal to 4 are not mathematically equivalent. They are not the same statements. Yes? Okay. And then, of course, I have this scenario. What about this? This one is true. The other one is also true. Yes? Yes? Okay. So here, I would say x equals to 2 is a necessary and sufficient for x3 to be 8.
Yeah, it is.
But of course, which one I prefer? I prefer to work with the simpler one.
Yeah, but I mean, being necessary means that this has to be the case. Sufficient is like if this
Yes,
is not the case,
yes.
then the other one can't be true.
Okay, but I mean they are different words.
Yeah, of course.
You cannot say that, okay, I use only the word sufficient, not
No,
necessary.
yeah. But-
Do you understand what I mean?
Yeah, but logically, if something is a necessary condition,
It means that if that thing does not happen,
Yeah.
then the other one does not happen either.
but it's like being sufficient kind of baked into being necessary? Because can something be a necessary condition without being sufficient?
No,
as well?
as far as I understand, the answer is no.
Okay.
That's exactly the difference between necessary and sufficient conditions. So we cannot reduce this to one word. You say that, okay, I just take this word and use it for both of them, because I don't see that. That's what I'm trying to. You have to convince yourself that this is not exactly the case. Okay, so is that understandable? Yes? Okay, so this is something I want you to know by heart. I mean, if you want to be good, the tables you need to know by heart. But then I want to go to another exercise, which is actually very important for our purpose, and that is this exercise. Construct the truth table for the following compound prepositions. So I have different connectives, and then we want to make it up. It's boring, but it is necessary. You need to do it once and learn it. Okay? So we want to set up the table here. Okay? So okay, so the first one is P if P then Q. Okay, okay? Sorry, Q. Okay, I will solve the first one myself to describe for you. So how many atomic prepositions are involved? Only 2. So how many rows I need in my table? 4. So, but the point is that you have to construct them little by little. So PQ are the atomic ones. So this is T, F. Of course, here it doesn't matter if you write Q first. It doesn't matter. But let me just stick to the convention. So sorry. By the way, it doesn't matter even if you start with F and then T. Yes, but let us conventional write this. Okay, now if I ask you what this is a conditional. The hypothesis, the premise is an atomic one. The conclusion is another conditional. Yes? So I cannot immediately start to set up this conditional. Yes? Because if I want to set up this conditional, yes, I have to first set up the conclusion. So the first thing that I have to calculate, to evaluate, is Q, if Q, then P. Yes? And then I can jump to the last one. Yes, because I cannot immediately start this one. For starting this one, I need that. Okay, now can you tell me what should I write here? Be careful. This time, Q is the premise. This one is the conclusion. The first row is true. This one, true again, because this one is false. The first one is false, the second one is true. Here, false, and here, true. Okay? So then here, what is playing the role of the premise? P. What is playing the role of the conclusion? This column. Yes? So now your premise here is T. Your conclusion here is T. So the conditional becomes T. And here, T. Here, true. Here, true. So it doesn't matter what these sentences are even if the sentences are nonsense themselves, so the whole combination is always true. And this is called a tautology. Yes? I will talk about that, don't worry, because I'm just going ahead a little bit about this. A statement, a compound statement, which is always true regardless of which values you assign to the components, and it is true, that is called a tautology. And if it is always false, there is another name for it, it's called contradiction. I will come to this, okay? Don't jump ahead. But I want to wait for you. This might be a boring exercise, but I really want you to do it yourself first, because you have to, try to do this to yourself. The second one is easy. The third one is a little bit boring one, but do it once. The papers are there. If you want, you can take papers.
False and P is false. Is the statement true?
Which one, of course?
And is
No. And yeah, just rely on your intuition. If both the statements are false
then it's
and
true.
you're combining them with and,
Yeah.
yes,
That's-
I am Jafar and you are Babak. Is it a true statement? It's completely false. Yes.
Yeah.
At least when I say I am Babak and you are Parham, this is still wrong. Yes. Yeah. But let alone both of them are wrong. Okay, could you do that? I mean, this is not hard, but I mean, you have to be a little bit patient, I agree. But let us do it patiently. First of all, that is good, I made a mistake here. You see, what is the problem here in writing this? Yes. What is the problem here? There need to be we need a convention about putting brackets or not. Okay, this is important, yes. But there are two conventions. In principle, this is not even acceptable. If we want to treat them properly, we have to put pair of brackets around them. Okay, this is not very clear yet. Might be if we have time, I will talk about this a little bit because it is very connected to computer science. So when you're doing a code, you have to be very precise in your syntaxes. So you have to have a very well-defined syntax so that you can be. So, I mean, in principle, you have to put pair of brackets around them, okay? But for the time being, I will use two conventions. One convention is that the outermost pair of brackets, we remove them, if not necessary. The second thing is that the negation applies as little as possible, okay? This convention is needed. Here, to be honest, first, I should have written this first. Because, why do you think it is necessary? Because might be you interpret this negation like this. Okay? But, because this is very familiar to my eyes, I will never interpret it in that way because I already know this. Okay, so this is the convention. Negation applies as little as possible. So it means negation after P applies only on P, doesn't go further. Okay, so this is one convention. The second convention is that I will actually don't need the outermost pair of brackets. Yes? But you don't feel that because I didn't even start putting this there. But later, if we, I don't know how much deep we want to go to this topic, we might need that. But at least respect this. If you see negation, this negation doesn't interpret in that way. It interprets as little as possible, only applies to P. Okay. So hopefully you are not confused because of that. Yes?
But do we also, if the negation comes after an operator or after the connective,
Yes?
do we still...
Immediately after.
Yes, so like P and not Q.
Yes, exactly. P
Can we also...
and not Q. Yes, this means that this not is for Q. Yes.
Yes.
Yes. Okay. So even for example, this makes sense.
Yeah.
How should you interpret this? This means this and that. Okay? But we don't write this because the first negation applies as little as possible. So it only applies on P. And this one applies as little as possible. So even if I have this scenario, what does this mean? This means this.
But if it's negated P and negated Q, isn't it the same as P and Q?
This mean?
Yeah, isn't it the same as P, just P and Q?
No.
Doesn't it give the same answers?
No, you will see that. You have to be patient with it. By the way, you can refer to your intuition about these things because these are logic, and all mathematics is based on human logic. You know? So in principle, you should come up with, and you know that philosophers also talk about logic, but in written words and sentences. This is why we call it mathematical logic, because we can use the power of mathematics to do it precisely, yes, and do some calculations too. Okay. So that's why I'm saying that if you intuitively think about that, you should come up with the answers. But if the compound proposition is complicated, then it becomes hard. Yes. Okay, so now let us go to here. Not P. If not P, then Q and P. We want to draw the truth table of this compound statement. So tell me, what do I need? How many rows I need?
8.
No, here.
Oh, 3, 2, 4.
4. Because there are 2 atomic prepositions, P and Q. Then after that, I use connectives to construct this. Yes. So I still have P and Q. Then I have TT, FF. Then I have TF, TF. Yes. And then here I have to construct this little by little. So what should I first construct? Because at the end, this is of this type. This statement is of this type. The box is this, and the circle is that. Okay, so if I want to construct this, I need to know the box, I need to know the circle. What the box is not P, which is not still there. So I have to bring it in. Yes? And what do I need after that? I need the circle. So the circle is Q and P, so I have to bring it there. And after Q and P, I am ready to construct my conditional. So I just write this final form. Okay, you tell me. If you want to write not P, the only column concerned is the first column. Okay, so what is not P? This is TTFF. So not P becomes FFTT. Yes? And Q and P is conjunction between these 2 columns. So the first one is T, the rest of this is F. Are you with me? Okay, and then I go to the conditional. So don't let this name distract you. You just have F and T only. Yes? So, but this is playing the role of the premise. This is playing the role of the conclusion. So what happens with the first one?
True.
This is true. What happens with the second one? True. What happens with the third one?
False.
False. And what happens? False. So that is the truth table of this compound proposition. Is it right? Okay, so let us go to the third one. Again, I was a little bit confused myself here, so now let me use the conventions I told you. Is this pair of brackets necessary? Yes, because there is an arrow between them. Yes? So this is still necessary. Is this necessary?
Yes.
Yes, because of this arrow. Is this necessary?
No.
No, so let me remove. Yes? Okay, go here. Is this pair of brackets necessary?
Yes.
Yes. This is not the outermost, don't get confused, yes? Because if I take this out, then you don't know this is the conclusion of this one, or the whole thing is the conclusion of this one. So that pair of brackets is necessary. But what about these 2? No. Okay, so let us just stick to these conventions for simplicity of writing. Okay, can you tell me how many atomic prepositions you see? 3, P, Q, and R. So how many rows I need? 2 to power 3, which is 8. Okay, so I have to set up P, Q, and R. Okay, so I didn't explain my algorithm properly, but because we are humans, I hope that you understand. So how many T's I have to write here? 4 T's. And 4 F's. Yes? By the way, this is also itself a mathematical theorem that if you do this, you are considering all possibilities. But I hope that it is a very simple combinatorics, yes? So what happens for Q? What do you think I will do here? TT and FF, TT and FF. And then last one, TF, 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 and TF. Yes. So if you don't mind, let me draw some lines here. It's very, very bad doing things. Okay, so let me do it properly, okay? Yes. So let me do it here. P, Q, R. I will write it properly so that I don't need the horizontal line. So here I have T, 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 F, 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 F. Then T, T, F, F. Now please also check my calculations. If you see something wrong, please. Yes? I hope that you agree that every possibility is considered here. Yes? Okay, now try to, this is a, now you know what the trouble is. I will not have enough space horizontally, hopefully. So because what I need, I see that I have not P, not Q, not R. So let us construct it, okay? So there is no order involved, so you can do whatever you want to. I hope that we shouldn't do it from the beginning. Okay, so let us do it. Not P, 4 T's becomes 4 F's. And then 4 F's becomes 4 T's. Yes? Please check my calculations. The second one, F, F, T, T, F, F, T, T. Yes? The next one is F, T, F, T, F, T,
You missed on the last negation of Q, that's supposed to be true.
Negation of?
Q, in the last row.
Negation of Q here.
Yeah, that's supposed to be true.
Why?
Oh, yeah.
Ah, I started with 2 F's. Thank you, thank you. So this is 2.
No, that's right. That's right.
No,
the
that's
last
right?
one-
Ah, okay.
The last one is supposed to be a T, actually.
Ah, 2 T's, 2. Okay. I get it. This is T. Thank you very much. Because 2 F's, 2 T's, 2 F's, 2 T's. Yes? Is this the only mistake?
Yeah.
Okay. Now, which one you start constructing?
I just did the entire left side.
Okay, in one go. But let us try to do this one. So Q and not R. So Q and not R is which one? Q is this one, not R is this one. We want to do the conjunction here. So yeah, this is F because T and F is F.
Negation of Q, you're looking at.
What? Oh, okay. So negation R, yes?
Yeah.
Okay, thank you. Is these two.
Yes.
So this is still F. This one,
True.
true. This one,
True.
F. No, this is negation. This is the conjunction. This one, F.
False.
Yes. This one, false. This one, true. This one, false. This one, false. Are you okay with that? Yes? Okay, and then it is appropriate to do this one. So I would say that the left-hand side, I need a space. So the left-hand side, I mean this. Yes? Okay, so but now this is playing the role of premise. This one is playing the role of the conclusion. So which ones are I have to look at? These. So yeah. Which one is this one? T, F is F. These two? True. These two? F. These two? F. These two? T. These two? T. These two? T. These two? T. Left hand side. Yes? And what I need the right hand side. Be careful. The right hand side, not Q is coming first. This is a little bit, you have to be careful. So the not Q is coming first. So can you tell me now, not Q and not P, the other way around? Yes, so it is T, F, F again, T, T, F, F, T, F, 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 T, T, F, T, T, F, T, T. Which one was that?
Wait, I think you meant.
No, it's true. It's true.
Am I right?
Yes. No, it's true.
Okay, so what is the last one? I confused.
No,
T?
that's not true.
So let us check. not Q, not P. So this one. Yes, that is T. Am I right or not? Yes. And then the whole. Or proposition, yes. So what should I do now? Left hand side is my premise, the right hand side is my conclusion. So tell me, what happens here?
T.
T, T,
T.
T,
T.
T. Oops.
No,
Is it T?
yeah.
Okay. So it's always a T.
So it's
It's also a tautology.
a tautology.
Yes. Okay. I hope that we haven't done any mistake. But I want you to get the feeling. Yes. And I want you to feel it. The reason I want to do this because I want you to feel it is boring. Because I just want to motivate you for another step in our understanding, and that is the algebra of propositions. Okay. So that's why this is extremely boring if it becomes complicated. So is there any better way to do it? So we little by little we want to go to that. Okay. So if the next thing that I want to define is the notion of tautology, a compound proposition that is true regardless of the truth values of its components is called a tautology and is denoted by this LaTeX symbol. It is not a T. If you want to write it in LaTeX, it is a /top. You see, it is not a T. You know in geometry, if I say line L1 is perpendicular to line L2, this is the perpendicularity symbol. If you make it upside down, this becomes this symbol. It's not a T, it's similar to a T. And of course, by the way, in many textbooks, they write T, I don't know, a bold T for tautology. Okay, and this one in LaTeX is perp, means perpendicular. Okay, but anyway, when I want to write it, it is not recognizable, it's not a T, so we can take it as a T. So that's the meaning of a tautology. Read it top. And then I didn't know that these are coming to be tautologies, but if I haven't done anything wrong in this calculation, so this compound sentence is a tautology, regardless of what you assign for Q, P, and R, the answer will be always true. And then, so I will skip this example, because now I hope that this you can be done. You can write it down. By the way, I put this PDF file below the video, in the description below, so you can just take it and just do it. So let us skip this exercise because that is very similar to this one. If I want to prove that this is a tautology, I set up the table. The last column should be filled with all T's. Yes. The next example is the next definition is a compound proposition that is false regardless of the truth values of its components is called a contradiction and is denoted by this. Read it as bottom. But the LaTeX one is not bottom, it is /perp, means perpendicular. And if you don't mind, I will also skip this exercise. I wanted to show, might be, let us not skip this exercise. Let us do that, okay? Because we didn't have any contradictions so far. So let us do this. We want to prove this is a contradiction, okay? So how should I do that? First of all, I want to use the conventions I just told you. So I don't want to write the sentence as complicated as you see there. So what can I do? So I would write P or Q, and then I will have and I will write not P and not Q. So I don't need to put those extra pairs of brackets. Okay, so let me just do it fast. So P, Q, I have only 4 rows. T, T, F, F. I have T, F, T, F. I need not P, which is F, F, T, T. I need not Q, which is what? T, F, T, ft, and then I need p or q, which is t, 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 f, and I also need not p and not q, which is between these, so it becomes f, this becomes f, this becomes f, this becomes t, and then finally and between these two, so the whole. So this becomes f, this becomes f, this becomes f, this becomes f, because I am doing the conjunction. And everything is there f, so that is what? A contradiction.
And what makes this a or like what defines a contradiction?
The definition of the contradiction is that the last column is always f. It means that for any assignment of the individual components there, it doesn't matter. The answer will be
Like supposed to map that to some more intuitive or like combination.
yeah. For example, I can say
The contradiction is that like not Q implies not P. What was
no. That not Q implies not P is called contrapositive of another implication. Yes, we will talk about that as well.
So contradiction is just like.
But for example, the door is open and the door is closed.
Yeah.
I mean, two things cannot happen simultaneously if you if you compound them, combine them with the conjunction.
So
That
if
would
it's
be.
intuitively, I mean, it kind of makes sense that you.
Yes, because
P
intuitively,
or,
yeah, exactly.
P or Q.
Yeah, I actually constructed this intuitively. Yes. Anyway, any questions here? Okay, so